So Sasha Zhiboedov will tell us more about the analytic matrix Bootstrap.
Hi again, everyone. Shall we start? Yes, I know that some of you were not here yesterday, so let me quickly recap a little bit. What are we doing and what's the goal? So we consider a theory, which is a gap theory. It has an S matrix. Theory is quantum and strongly coupled. We don't have a Lagrangian. We don't have a coupling to expand, and we want to understand what is the space of theories. There are many physical theories which are in this class, say QCD. So we want to find an S matrix. We want to solve the theory, or less ambitiously to say something non-trivial about, make some predictions. So yesterday what we asked was the following question. We know that if you have an S matrix in high dimensions, and your S matrix has extra symmetries, there is a theorem by Coleman and Mandelstam that it has to be trivial. So we can ask a little bit more refined question, which is that we know in 2D there are S matrices which are not trivial, but they're factorizable. So there are S matrices where you have non-trivial scattering, but you do not have a particle production. So yesterday we asked the following question. Could we imagine a high-dimensional S matrix where there is a scattering and no production? And the answer to this question is no, and it's given by this Arcs theorem from 1965, which we proved yesterday. So let me just recall what were the main players of the proof. And then today what we will try to do is that, okay, if we assume there is no production, we show that such S matrix does not exist, but let's say there is some production. Could we say something about amount of inelasticity, amount of production, which is required by consistency? It's the first question. And the second question, as I emphasized, the theory is strongly coupled, so there is no small coupling. But we learned recently from the conformal bootstrap that if you don't have a small coupling, sometimes you can find within a theory some kind of perturbative expansion. And in the context of conformal bootstrap, the perturbative expansion was in one channel, it's a small distance operator product expansion, and in another channel, it was an expansion at large speed. So in every theory, you have a spin. You can take spin of things to be large, and you can expand it 1 over speed. So this would be also true more or less here. And yesterday, yes, and it's all some of my talks based on I'm going to work with Amit Severets here. So yesterday we talked about this work by Axe from 1965, and today we will move 1 year forward. And this idea in a slightly different form was essentially discussed by Alex Drag in 1966. This first long time ago, so then maybe the focus was slightly different. But in the modern terms, what he discovered or what he found is an analytic bootstrap-wise matrix in terms of large spin expansion, modulo some things. So the main player is we imagine a theory with a stable scalar particle of mass m. The S matrix takes this form. Then we discussed yesterday analyticity, unitarity, and crossing. These are the 3 things we want to impose. Analyticity, unitarity, and crossing. And as we discussed, this, if we consider 2-2-2 scattering, so this operator becomes a function of Mandelstam variables. And what we considered yesterday is a Mandelstam plane. And we found that it looks like this. And there are physical regions, whereas scattering corresponds to physical angles. And then we found what is known as Landau curves, which is a region where the double spectral density or imaginary part of imaginary part is non-zero. So, and it was somewhere here. So if we denote discontinuity with respect to S variable or T variable with sub-indices, there was a spectral density, which is TS. And then we found that the spectral density has a support in this region, and then we imposed crossing and showed that no production leads to trivial scattering. So now today I would like to develop an attempt to now analyze if theory has a production, what happens, and let me write sort of key formula from the previous talk.
Sorry, Sasha.
Yeah.
Before you go ahead.
Yeah.
So the fact that the spectral density is different from zero in that region is independent of the assumption of production of modes.
Yeah. So this non-zero spectral density follows just from the fact that 2 to 2 thing should be non-zero, and then basically this the contradiction comes from the fact that if you assume no production, you conclude that the spectral density is 0, and then you get that this guy has to be 0. That's the basic argument. So the basic trick was due to Mandelstam, and who considers a unitarity relation for this T matrix, and we consider it in the region where there is no production of particles. So say S is 4m squared less than 16m squared, and then he managed to analytically continue this relation, and it takes the following form in 4 dimensions. Spectral density is equal integral of angle variables, some region. Here there is a discontinuity of the amplitude times an amplitude, function of this angle. And there is some known kernel, which is a function of z, eta double prime, where z is related to t. Okay, so that was what we did. And so today's the idea would be the following. So we will try to look at this again, this elastic unitarity relation.
Sorry, what is the lower end of the integral?
Yes, thank you. I was, again, this is, I tried to explain it previously, so it is 1 plus 8m squared over s minus 4m squared. It comes from the fact that we assume that analyticity of the amplitude has a structure, so we have a cut 4m squared, and it's crossing symmetric dual, and that's it. And so when the same for the t, and so when t is equal to 4m squared, you expect the cut, and this is to get 4m squared, so this is where the cut starts. So there is a U channel, but because the particle identical, they all contribute the same. So the idea is that since we have a rotational symmetry in the problem, it's standard to expand the amplitude in terms of spherical harmonics or Legendre polynomials, generalized Legendre polynomials. So we can always take the amplitude and write it like this. So this is a definition. This is, if you wish, a definition of this FJs, and so in the left-hand side we have S and T, but on the right-hand side, these are basically Eigenbauer or Legendre polynomials. So instead of T, we essentially have a J. So we promoted T to J here. So these guys are called partial waves. And they define, well, as you might guess, you just integrate over angle with an orthogonal measure against this Legendre polynomial, and you take your amplitude and you plug it's written there. So T as 1 half S minus 1 squared. Now, this you can ask where does this partial wave expansion converges, and what are the properties of this FJs of S, analytic properties, and they inherited fully from the properties of the scattering amplitude. So analyticity of the scattering amplitude implies that this partial wave expansion converges absolutely and uniformly inside what is known as a Lehmann-Martin ellipse. Which is defined as follows. So you take this angle plane, and the ellipse takes its form. So this is a cosine of the ellipse, and the maximal major semi-axis is given by this A1 of S.
Sorry. So here, basically, from the first to the second, you are using orthogonality relations.
Yeah. It's just the fact that these PJs, they are orthogonal polynomials with these measures. In 4 dimensions, they're Legendre polynomials, and they have a standard measure. Let me maybe also write for simplicity. That's because maybe I'll mention it before that. And the simplest and maybe useful to think about, and in D equal 3, these PJs are nothing but sine J of theta. That's very simple.
Sorry, then you're trying to understand in which region.
Yeah, you can ask in which region this partial wave expansion converges.
FJS.
This sum.
Oh, yeah, okay.
And FJS, it will also have cuts. One cut which are completely inherited from here. So one cut will start at 4 and square, another cut will start from 0.
Sorry, is that supposed to have also analyticity in the spin J?
This one?
Yes.
It will. We will come to that. So it will. Well, yeah. So this is. It will have analyticity. So far as this J, as you can see, it's just an integer. So here it's 0, 1 to infinity. It's an integer number. So you can ask what is recall that this unitarity relation, which is written here, was the same as S dagger AS is equal to 1. What does it? Which form does it take in terms of this FJ of S? And the form that it takes is simply that, so as I told you, so from this formula you can figure that this FJFS in the S plane, there is a cut starting from 4 and square, and there is a cut starting from 0. That's an analytic structure of FJs. And moreover, as we discussed yesterday, there is this property of Hermitian analyticity of the amplitude, which becomes a statement that Fj star of S plus I epsilon is equal to Fj. Again, as usual, so if you approach a physical process, it's from above from the cut, and if you approach the cut from below, it describes and conjugates its matrix, which is this. Now let me write the unitarity relation. And the way you do that, you just integrate, again, you sandwich this with two particle states, and you consider them as states of some angular momentum. And what you get is the following relation. That if you go along this, if you consider the discontinuity along this cut, so the imaginary part of partial wave has to be larger or equal than s minus 4n squared, the d minus 3 over 2 square root of s times j squared. That simply follows from the definitions, and then you plug and integrate. Recall also that so there is this absolute value in the right-hand side, which is simply this, and there is this larger, greater or equal, and so greater comes from the fact that, as we discussed, for general energies, we have not only 2-to-2 process, but we have extra channels. So on the right-hand side, but they all contribute positive definitely. So the right-hand side, if we just restrict to the 2-to-2 process, can be less on the left-hand side. And the second thing is we know that when there is no production, so when there is elastic unitarity, so again for s, 4m squared, 16m squared, we have here an equal sign. Now we can note what Fernando alluded to, which is that a priori these partial waves are just defined for integer spin. But as was realized in the 50s, it's a very good idea to think of spin as a complex variable. And recently it was realized in CFTs that it's also a good idea. And the reason for it is basically that there is a canonical and unique analytic continuation in spin, which is inherited from analytic properties of the amplitude. And then you can, by thinking about spin as just not an integer, but some complex variable, you can learn some interesting things. So the way the way to perform this analytic continuations, there are many ways. Let me just tell you one. And this analytic continuation in spin and writing the partial waves as a function analytic in spin is known as, in the modern Bootstrap, as Lorentzian inversion formula, but in the 50s they're known as a Froissart. It was done in 63 and then I think in 64 by Zhiboedov representation. And so they're essentially identical in CFTs and amplitudes, and you will hear probably from Fernando how this thing plays out in CFTs. So the idea is the following. We recall that we discussed the amplitudes are another property is amplitudes, which follows from the locality of quantum field theory with polynomial boundedness. And we can discuss when it was proven, etc. But if you assume the polynomial boundedness of the amplitude, you can write what's known as dispersion relations. So let me just assume that, so how do? We take an amplitude, st, write it as a Cauchy integral. Right, so this is a trivial identity for general point. And then we deform the contour we pick the contribution from the cuts. So there is a foreign square cut, the dual cut. So the contribution, I will only write the contribution from one cut. The other one is trivially, everything's generalized trivially to the other one. Here, to do this thing, we deform the contour. So in principle, there is a contribution at infinity, which you should worry about. So if you can drop it, then all which is left is a contribution from the cut, and Ts is a discontinuity. Okay, this is a dispersion relation. So now let's take this dispersion relation and plug it in this formula. So if you plug it in this formula, you get the following result for GFS. You get the integral over, say, here actually I want to use dispersion relation in different variable. Sorry, let me.
Sorry, in order to be able to drop that integral, is it enough with polynomial boundness, or do you need some stronger decay?
No, it's here, yes, of course. So here, for example, to write what I just wrote on the board, I assume that it decays.
So 1 over.
It decays, it just goes to 0, right? So the t goes to 0 in a large t. Now, in general, this is not true. It will behave like a polynomial, so we have to do subtractions, and you can do that, but it slightly affects, but not too much. So now take this dispersion relation, plug this in this formula. So what do we get? We see that now we have a here integral over this variable z, which enters through t, and all dependence on t is now in this prefactor. So similar to what we did before. So what we get is actually an integral, say 4 squared, infinity, dt, which is this integral. And here we get something which is known as a, so we have a, sorry, we have discontinuity in t. And here we get the following integral, which is integral from minus 1 to 1, dz, 1 minus z squared, d minus 4 over 2, h of z. Here we get t prime minus t as a function. So you can perform this integral, and this integral is related to so-called Q Legendre polynomials. So as you know, Legendre polynomials, they satisfy second-order differential equations, and this second-order differential equation has two solutions. One is a familiar Legendre polynomials, another so-called Q Legendre polynomials. So the property is that they have a cut. So they have a cut between -1 and 1. So where Legendre polynomials are analytic, discontinuity of this Q polynomial in this cut is related to Legendre polynomial, and they're analytic otherwise. So I will maybe write, for example, recall that Legendre polynomial in 3 dimension is given by this formula, and say in d equals 3, Q Legendre polynomial is equal. So the crucial property of this thing is that it will be an integral. So you see that if we now replace this thing by, sorry, let me introduce here Z prime so that you don't get confused. Where Z prime is related to this variable over V, which we're integrating. The crucial property of this, the crucial property that you have to have in mind about this Legendre polynomials, and this is true in all dimensions more or less, is that when we integrate over this discontinuity here, these Legendre polynomials, they behave as t prime is a minus j. So they behave, think of them as just powers in t. So this formula, it is, if you look at this, for example, this polynomial is manifestly analytic in spin. And
sorry, they behave like that for a small t prime, for large t prime.
Sorry. Thank you, Fernando. Please ask me more questions. So, large t prime. Yeah. The idea is that when t prime is large, z prime is the same as t prime, and this is the same as z to the minus j, t prime minus j. Okay, so I guess the big words you can say is that in quantum field theory, and the same is true for CFTs, even though we started with partial waves as being objects which is defined for integer spin, everything is defined. You should think about complex J-plane, and it follows from analyticity and locality from locality of quantum field theory. So therefore, if you have now this variable J, which is which you can take whatever you like, you can start thinking, can you develop a kind of some kind of perturbative expansion at large speed? So, and the answer to this is yes, and this is what Drag did his, or started doing in his paper. Another review now. So the idea is now, since we have a strongly coupled theory, let's try to build some kind of perturbation theory in spin. And compared to CFT, it will have some interesting twists. So how do we do some kind of large spin expansion? It will has 3 steps. So first, I would discuss what is, let me call it the threshold expansion. This would be the analog of B. For example, it was discussed by Bross and Yago Nitzer in 81. Then we will use elastic unitarity to turn this threshold expansion into some predictions about amplitudes, some elastic unitarity. And finally, we will use Brossard-Weber formula. For Fj to turn it into a large J expansion. So this would be the scheme. So let me explain what it all means. So what is a threshold expansion? Has So again, as you hopefully as I emphasized enough that the problem is strongly coupled. We don't have a coupling. So if you want to do something analytic, we need to find the small parameters, something that we can expand. And one parameter which you can take large is the spin. As I told you, I haven't explained why it will become a weakly coupled or some kind of expansion. But there is another nice parameter which you can take small. What is this parameter? So let me rewrite again the elastic unitarity condition. So again, we take the imaginary part of this amplitude to be equal to the square. And I told you that for, let's say, S in this region, in terms of partial waves, this simply becomes imaginary part of JFS is equal S minus 4m squared d minus 3 over 2. So you see this factor, power requires some explanation, but you see this factor here, S minus 4m squared. What is the physical meaning of it? Well, recall that what is when we sum over final states here, this sum over final states is as we discussed yesterday, integral over angles. So, and imagine that you have a 2-to-2 scattering. What is the minimal energy for which the scattering is possible? Well, it's S equal to 4m squared. Now imagine you increase a little bit. The phase space volume, which is available to you, is very small. So you can use a phase space volume close to the threshold, which is S equal 4m squared, as a small parameter. You can construct an expansion of the amplitude of this, and expand the amplitude in this small parameter. And the idea would be that the expansion in the small parameter, which would be the analog of a small distance expansion in CFT, through crossing and these bells and whistles will be translated to expansion at large speed in the crossing. So that's the physical picture, is that we have a small phase space volume, which is analog of small distance, and it will be translated to large speed. So let me rewrite this equation in a nice way. So I will write that the imaginary part is nothing but 1 over 2i f minus f star, and absolute value of f is f times f star. So let me divide by the right hand side. So we get 1 minus over 2. 1 over fjs. So we divide by this. F divided by the square gives 1 over star. 1 over s. And it's equal to s minus 4 squared. Now you can solve this equation. You see the point is that we have a cut. Let's think of function f. Well, 1 over f, it's an analytic function. So there is a cut starting at 4m squared, and then when you take discontinuity along this cut, you have this thing. So it's very easy to hook up a function. Which has this discontinuity, which is fixed. Plus, you can add to it something which does not have discontinuity, a polynomial or a pole, and that's the most general solution. So let me introduce this expansion parameter sigma, in which we can expand everything. So 1 minus s 4m squared So when S goes from square from below, sigma goes to 0 from above. And so the most general solution to this equations, I will write in a second, but already at this point you might notice something very cute, which is that often, well, in many contexts, odd dimensions and even dimensions behave in a slightly different way. And the same happens here, that in, you see that this S minus 4n squared in odd number of dimensions, it's a polynomial, and in even number of dimensions, it's a square root. And this is reflected in analytic properties of scattering amplitudes. Actually, they have a very different type of singularities in odd and even number of dimensions. So in even number of dimensions, it's a kind of square root type singularities. And in odd number of dimensions, it will be very different. For example, I will write it in a second. So I will write now a solution in odd and even number of dimensions. So in odd number of dimensions, odd D, you can write fj of S as a square root S 4n squared S over D. And here we write 1 over pi log of sigma plus Ej of sigma. So you see what happens is that when D is odd, you take the inverse, you cancel this factor, which is a polynomial, doesn't have any discontinuity, and then as you approach the cut from above from below, log has a disc I pi, so it exactly reproduces 1 in the right-hand side. And the curious thing is that and these guys are, if you wish, meromorphic. So they could have poles. And then you can show that the maximal singularity that they could have is, and actually that's, this will follow so from Crosser-Zhiboedov automatically, is 1 over sigma j. Here you have 1 plus whatever, A0 plus A1 sigma, blah, blah, blah. So you have this structure. And in particular, note that in 3 dimensions, for example, in 3 dimensions, this factor just vanishes. And if we do any kind of diagrammatic computation and using Feynman diagrams, bubbles, we are used to getting logs of power of logs, log S minus 4n squared. Note that here, non-perturbative, we get 1 over log, which is very unusual and very interesting, and people who are doing S metrics are very surprised by this fact. And then they have some arguments. Actually, this 1 over log is realized in physical theories. So the intuition you get from perturbation theory with getting logs is very wrong. You get 1 over log here. And in even number of dimensions, S minus 4n squared is a square root. It has a discontinuity, so the solution looks slightly different. Maybe I can squeeze it here.
So you want 1 over log plus b, and then that cannot be expanded or something, so it gets consistent with perturbation theory. Or?
It's non-perturbative. So it's if you try to do perturbation theory, it's actually, it's very easy to get it from, if you wish, it's a, Let's say you do perturbation theory, phi to the 4, you can get something like this, lambda log sigma plus 1. So you see that there is a region which is non-perturbative in lambda of the size e to the minus 1 over lambda, where this thing dominates. So when you take s to the 4n squared, this is very large, and the asymptotics is 1 over log sigma. But here it follows from unitarity and everything that you can expand in this parameter sigma, which is a natural expansion parameter. Now, in even number of dimensions, you get a slightly simpler structure. Get 1 over, and you get here this factor, square minus s, t minus 3 over 2, whole square root of s, plus bj of s. You don't need this log anymore, because let's now take an inverse. You plug here an inverse, you have a cut, you take a discontinuity along the cut, and you get precisely this. You give a number of dimensions. Is that clear? Okay, so that's the first step. So, and note another curious thing, that you could have thought that, okay, so there are some...
Sorry, I have a confusion. So this is certainly a solution, but couldn't you, I don't understand why the solution upstairs doesn't work for the even.
Which one? This one?
Yeah.
Ah, well, because you will not match this guy. This guy will have a disk, and disk of this guy will contain a log.
Sorry.
Yeah. And another curious fact which I would like to emphasize is that here I wrote ad hoc this coefficient, but actually, as you can see, the structure of the equation is such that this coefficient is completely fixed. It's fixed by unitarity. We cannot, because you have to reproduce this guy. This is universal coefficient, and the same here. And we will use, in a sense, this universality to do some predictions. So this expansion, it might be useful, I don't know, in general. It might be useful for Bootstrap, and I will discuss one aspect of its usefulness. So what happens is that I told you that the idea would be now to take this amplitude, to take this threshold expansion for the fj's, which also becomes a threshold expansion for amplitude itself, and to plug it into Froissart-Gribov formula. So it is, as I discussed here, we have this formula for f of j's in terms of discontinuity of amplitude in the dual channel, and then we will see, as I will try to show you now, that the threshold expansion becomes a large spin expansion. I haven't shown you that, so that's the next idea. I hope it's clear. So we have a threshold expansion here, and now crossing Froissart-Gribov turns a threshold expansion into a large spin expansion in the dual channel. That's what I want to show. So threshold expansion is large. To do it, let me write maybe a version of this Froissart-Gribov formula in 3 dimensions, precisely with all the coefficients, so that you might see it better. For example, the simplest form of this formula takes in 3 dimensions. So you get this. You get the integral over discontinuity. Infinity. dt over square root t plus t squared. And here we have s minus 4 squared to the j, t to the j. So this s minus 4 squared to the j is nothing but this statement. T to the j we already discussed, and there is also a factor here, 1 over square root t. This is simply, and here we have discontinuity in T. This is T. So now the point is, and you can check it in all number of dimensions, is that you see that the integral starts at 4n squared. So if we can rewrite everything in terms of the expansion around this 4n squared. For example, let me introduce s equal to 4n squared times s hat, because it's dimensional things. T equal 4n squared times t hat. You see that you have this integrals from 1 to infinity in t hat, and you have an exponential suppression, 1 over t to the j. So you see that this integral, as you take j to be very large, it localizes close to the lower region. And lower region is nothing but a threshold. Therefore, you see if you plug a threshold expansion here, and you take a large j limit here, it turns the threshold expansion in one channel, t close to 4n squared, into large j expansion in the other channel. So this is the basic idea of this thing. So now, not only this, which is correct. So you can go ahead and start computing these corrections. But there is another nice thing that happens, which will help me. So I will discuss a little bit further than this expansion. And naturally, what will happen is that, as you will see, these powers of sigma will turn into powers of 1 over speed. So that's how it will work. But there is one nice thing that happens still, is that recall that again, if we want to talk about inelasticity of the amplitude, inelasticity of the amplitude was encoded in imaginary part of f. Right? Remember this: im f larger or equals than f squared times this factor. So if you take imaginary part of f, all these things here, the analytic in S, so imaginary part of f comes from taking a discontinuity here. Otherwise, it's all fine in S. So if you take an imaginary part of f, you get the similar formula. Everything stays the same. But here you get the double discontinuity. Well, double spectrum density is a function. So, okay. As we discussed it last time, it has some nice properties. It starts at Landau curve. It's an interesting object. And so what happens is that now, here, as we discussed, as we have integral over dt.
Sorry, but this is a double discontinuity in S and T.
Yeah, yes, it's S and T. So that's a double discontinuity in S and T.
Which is a bit different to what we do in CFT.
Oh yeah, it's different. Yeah. Double disc in S and T. So this is the same formula. And recall that last time I tried to argue through elastic unitarity that this guy has a support. So if you take, it has support only for, say, t larger or equals than something called, let me call it t2 plus s. And this t2 plus s is what we started again today, this Landau curve that there is, that in the Mandelstam plane there was some support for the spectral density, and it was different from for n squared. And so again, you see that if you have an integral over 4n squared to infinity, the integral, because there is t to the j at large spin, it's dominated by a lower limit of the integral. This time, the lower limit corresponds to a Landau curve. And so you can compute, in principle, you can compute, if you have an expansion of a double spectral density close to the Landau curve, you can plug it here, and it will turn itself into expansion at large spin. Is that clear? It's always because, so you take this, say, if you have an integral of the type dt t naught t minus j, you can write it as an integral of t naught plus delta t minus j. So there is always a suppression by t naught minus j. And then, if you rescale, and then you have an integral dt from 0 to infinity. And here you have 1 plus delta t minus j. And as you know, this is a supported region which is controlled by t. It's very well known. Okay, so then, Then the question is, can we compute the double spectral density close to the Landau curve? And the magic is, again, if you take a threshold expansion, plug it into this elastic unitarity condition of Mandelstam that I started today, again, then you will get an expansion for rho close to the Landau curve. So the lesson here is that if you take elastic unitarity, you take a threshold expansion, and convert it, and this is elastic unitarity. And threshold expansion is converted to expansion of double spectral density close to the Landau curve. And then, again, the idea is to use crossing and Froissart-Zhiboedov formula to convert it into large J expansion for imaginary part of f of j. So you see that from what I told you that if I take as my starting point, for example, let me now go to 4 dimensions. So we'll go to d equal 4 here, and take you see that the simplest solution here, which is the solution for leading j, would be to have a singularity of the type 1 over square root. It's again something we are not used to in perturbation theory, but that follows from unitarity. So you can take.
Sorry, I am slightly confused.
Please.
Because you said that B itself is of the order 1 over sigma to the j.
Right, so.
But we are in a regime in which sigma is small.
Exactly, yes. So let me take j equal to 0 now. And consider, so I want to, yes, I haven't explained it properly. So I would like now to consider an amplitude which is, to consider a simple asymptotic which is allowed by this solution, which is in a sense, it's in a sense maximally strongly coupled because it's maximally singular close to the threshold. So I want to consider this toy model. And what I'm saying is that the maximal singular behavior, which is consistent of unitarity in 4 dimensions, is this. And this behavior was also observed in the numerical bootstrap work by Paulos, Benedones, Toledo, Andreas, and Vieira. And the coefficient 1 here is fixed exactly because this coefficient is fixed. It's the same coefficient. And now I want to show, to take this first term and the threshold expansion and run it through all the things that I told you about and see what we get for the large spin expansion of f and imaginary part of f. So now we take this guy and just plug it everywhere. We plug it everywhere we could plug it. So the first thing, I don't, it's something else, sorry. Be fine. Fine, okay. So first step, let's plug it into elastic unitarity. So then what you get is that we have an, as I told you, we have this integral, rho is equal the proportional, let me write, integral from dA to 1 from a1s infinity dA to 2 a1s to infinity. And if you've been yesterday and hopefully today, you remember the crucial fact here was there was this theta function z minus theta plus times discontinuity. So this is exactly what produces this Landau curve. And so now if you take rho close to the first Landau curve, which is you take z close to whatever 2a1 square s minus 1 plus z hat, you see that both of these integrals are localized close to the threshold because of the theta function. So what happens is that theta 1, if we write it a1 s 1 plus theta prime hat double prime is so if you take rho close to the first Landau curve, which is you take z hat to be small, then you see that this theta function becomes theta of z hat minus theta prime minus theta double prime, where this is the hats, where the integrals for dn hat dn double prime goes from 0. So they are localized close to 0. And there you can compute the leading term in the expansion. And for this amplitude, you get that close to the Landau curve, rho s and t behaves as a square root, say, so it behaves as a square root so it vanishes as you approach Landau curve, and you have the prefactors, which you know. So now let me take, now we have everything in principle. I can take this, have discontinuity close to the threshold, so I can plug it here. I have computed now, I plug this into elastic unitarity, compute the expansion of rho close to the Landau curve, and I can again plug it to Froissart Zhiboedov, and we can compute in this way the leading large J asymptotic of partial waves and its imaginary parts.
Sorry, maybe something a bit
Yes, please.
silly. So don't we know that rho is the discontinuity of s, the s discontinuity of tt?
Yes, so this has a 0 discontinuity.
Around,
So the double discontinuity is 0 of this guy.
yeah, sorry, yeah, of course.
So the idea is that you started with a discontinuity in one channel close to the threshold,
Yes.
and elastic unitarity tells you that there has to be double discontinuity close to the Landau curve, which is fixed in terms of this guy. And its form is fixed. And now we can basically plug into this formula and get the following result. So everything is ready. Now let me just quote you the result. And this will be an interesting result. So you get the following thing, that basically that maybe I'll just quote the final result. So you get as I told you that the fj of s is localized close to the lowest threshold. So you always get this kind of factor of sort of qj at z. Okay, let me just quote the final result. I don't have much time. So if you go through this exercise, that's what you get. So and let me just rewrite again that the unitarity condition tells you that we have in 4 dimensions this, and if there is no inelasticity, there is a quality sign. So it's natural to consider the ratio of this thing. So let me consider the ratio. And the claim is that the threshold expansion, you can compute this ratio at large spin. That's just what we did. And, well, it has some form, which so it has some p-factor, which is a polynomial in S. Let me write it. Almost done. Where if you forgot S equal to 4n squared times S hat. This is S hat. And most crucial fact that you get from all this consideration is you get the ratio of these Q polynomials, which evaluate at the border where the threshold for imaginary part starts for the discontinuity, and the threshold for the double discontinuity, which controls the spectral density. So we have some Landau curve here, and we have some ratio here. So so we get, if you plug everything, that z direct is equal 1 plus 8 over this one. And z dual is 1 plus this is follows from the this just follows from the followed from the shape of Landau curve and from the form of the discontinuity. And now the point is that as you take so as I told you this Legendre polynomials behave like powers in Z. And what happens is that if you take S to be large, you find that the ratio of this guys is such that this is much larger than 1. So this is much larger than 1, and it's fixed in terms of the inequality. So this is the result. And recall that the fact that it's large, the fact that it's equal to 1 corresponds to elasticity. So if it's much larger than 1, it means that the imaginary part is controlled by inelastic effects. And moreover, so it's at large spin, the scattering partial waves are mostly inelastic. Their contribution much larger than elastic. And the expansion of this inelasticity to elasticity admits a large J expansion. So that's a punchline. And now you can start expanding in spin. So there is some perturbative expansion of this in J. This is the leading factor. And again, the motivation of this came from the fact that in this numerical bootstrap, they considered certain ansatz and maximized the coupling, and they got that their scattering looks like purely elastic. So the question is, what's going on? And here, so this is one thing you can complain about is that, okay, this is asymptotic in J. So sorry, we're expanding in large J. What happens at finite J if you want to compare to numerics? And there was actually, I don't have time to tell, but there was a paper last year by Roy and Martin. So paper by Martin and Roy, who addressed this question. So you can essentially try to use polynomial boundedness because you have inversion formula. Inversion formula is exact. You have polynomial boundedness of the amplitude. You can estimate the error. Start playing these games. So yeah, thank you.
Questions?
So, this expansion in 1 over J, is it convergent or asymptotic? What is known about it?
I think I would expect that. So the whole, it might be asymptotic as it was in the conformal bootstrap case. I don't know if your number is correct, but I assume that whatever. The right way to think about it is that there is an inversion integral which is convergent and non-perturbative, and then if you're careful enough, you can always take care of all the non-perturbative effects. I think usually, at least in CFT with Fernando, we observed that large J expansion is asymptotic, but you can square out some. But then there was a way, if you think about the inversion formula, you can see from the start that there is a way to think about it in which everything is convergent.
Yeah, I think in CFT, if you consider any perturbative theory, then you have these things are all asymptotic.
Yeah.
But in a non-perturbative one, they are supposed to be convergent and given by the integral, by the inversion formula. But yeah.
So I suspect here it will be.
Okay, let's make a session again.